Hi everyone, I am Isabel Dominic de Malanta, here to present our paper entitled Improvement of Trajectory Errors on Remote Controlled Differential Drive Robot via Mobile-Based GUI through Bluetooth Connection. The demand for these mobile robots has been visibly increasing throughout the recent years, much as more especially when the health protocol nationwide to worldwide lockdown for pandemic was implemented by the government. These mobile robots are contributing great help and assistance to the overall well-being of people, specifically in terms of health protocols and prevention of the spread of the viruses. So the main focus in logistics service assistive robots should be the trajectory planning, which prevents the collision, maneuvering difficulties, wrong destination point, and many more. Achieving the desired trajectory is important to ensure the results of quality performance, ease of navigation, high operating time, performance efficiency, and other aspects needed in various fields. The need to personally control these mobile robots is achieved by implementing the remote controllers that offer ease of control and utilization to the users. To ensure the efficient implementation of the said technology, the design of the controllers is one of the most important aspects. Hence, the paper focuses on acquiring the best controller design based on the navigation to the desired trajectory following a linear path and rotational path testing on varying robot speed. The researchers mainly aim to improve the ease of navigation of a logistics service robot. For the materials, the researchers designed two different controllers, a physical joystick controller and a Bluetooth-based controller application that is able to maneuver a differential drive robot which serves as our logistics service assistive robot. The system architecture is as shown below. So the purpose behind the two different controllers is to compare the results as to which of the two controller is more effective in the aspect of ease of control and navigation to the desired trajectory. As mentioned a while ago, one of the most important aspects in remote controlled robots is the ease of control to the user's desired destination. In order to support the study, the testing methods will be discussed in this part. So the figures in the screen show the testing methods that the study make use of the linear path testing and the rotational testing. For the linear path testing, the robot will be controlled from point A to point B with a distance of 5 meters. While for the rotational, it will be controlled from angle A to the angle B. The trajectory error will be obtained by measuring the deviation from the final position of the robot to the end point of the track. So moving on to the results. The succeeding tables show the summary of the collected trajectory error data in the linear path testing using Bluetooth app and joystick respectively. The linear path tests include 5 different speeds of the robot: 0.75 meters per second, 0.5 meters per second, 0.35 meters per second, 0.25 meters per second, and 0.15 meters per second. The speed was changed by changing the code of the robot. For each speed, the researchers performed 15 trials. In conducting the rotational tests, the robot was to be rotated both left and right 90 degrees while the starting and final angle was recorded. The difference between the starting angle added with the 90 degrees and the final angle was the recorded deviation angle. The succeeding table represents the average deviation angle of 15 trials recorded for each speed of the robot, together with the time it takes to rotate left or right for both modes. Based on the summary of the data that was collected and presented, the trajectory error was improved by using the Bluetooth mobile app developed. Looking at the table, at speed 0.75 meters per second, there is a 60% decrease at the trajectory error from the Bluetooth mobile app to the joystick in the forward direction, and a 54.9% decrease at speed 0.25 meters per second moving in the backward direction. The probable explanation for the only 2% increase of the trajectory error is systematic errors such as inconsistencies in the caster wheels, uneven flooring, and the sudden high acceleration of the robot at the start of its movement. Overall, the trajectory errors recorded while using the joystick controller is higher compared to the trajectory error recorded when using the Bluetooth mobile app. Using the Bluetooth mobile app for the maneuverability of the robot allows for a less or minimal human error. In using the joystick, the user is required to hold the joystick button upward if the user wants to control the robot to keep moving forward, and to let go of the joystick button if the user wishes to stop. While in using the Bluetooth mobile app, once the forward button is pressed by the user, the robot will already keep moving forward until the stop button is pressed, and this allows less human error in conducting the linear path testing. With this, it can be concluded that the Bluetooth mobile app allows for easier maneuverability of the robot. For the rotational testing, the most significant probable cause for the trajectory errors present is the human error, especially at higher speeds, since the user needs to press the stop button much quicker when the robot rotates 90 degrees. In addition, the robot also does not instantly stop when the stop button is pressed, since there is a momentum present. And that concludes the presentation. Thank you everyone for listening.